Hello everyone, in this video I'm going to show you how to design a common emitter amplifier, common source amplifier with source degeneration. So unlike before, uh, I'm going to connect a resistor to the source terminal of a MOS transistor. There are many reasons we need to do that. First, you want to stabilize the circuit. This is one reason. Another reason is we may use the bias circuits. We may modify the circuit and design a common gate amplifier. So to start with, we choose this MOS transistor. This MOS transistor has a threshold voltage 1.9 volt, so not too bad. So what we can do now is, first, we assume there is no degeneration at the emitter. So in this case, we connect all the way direct. Connect the source all the way to the ground. And we randomly put the resistor. And the resistance here is 100. Normally, at saturation, the drain to source voltage is not going to have too much influence on the drain current. So now, what we are going to do now is to make sure the circuit satisfies two conditions. One is so-called the cutoff frequency, the other is the saturation. The cutoff frequency, in order to satisfy the cutoff frequency, we need to make sure the gate to source voltage is always greater than the threshold voltage. The threshold voltage, as you can see here on the model, is about 1.9. Yeah. Given that there's no body effect, then it is 1.9. So what we can do is we can use the voltage divider to divide this 10 volt, and we don't need the excessively large gate voltage. We just make sure it is sufficiently large than the threshold. That is enough. Say now the threshold is 1.9, right? We can just make the gate voltage 2 volts, in which case the gate to source voltage is also 2 volts, while the threshold is 1.9, so we have satisfied the requirement. So we can do that. So one of the ways is we can do this. So in which case I will use 2 mega ohm here and 8 mega ohm here. So here 8 mega ohm. So I can guarantee the voltage at this point is 2 volts, because the voltage divider here, 2 divided by 10 is 0.2, and times 10, then there will be 2 volts here. So now I'm going to check the biasing first. So to check the biasing condition, I need to choose operating point analysis. So as you can see here, it's difficult to see because you cannot see the node voltage. I suggest we label the net. The drain. The source. The source voltage will not appear. So in this case, you get 7.15. The gate voltage is 2 volts. This means the gate source voltage in this condition is also 2 volts. The gate source voltage minus the threshold is 2 minus 1.9, which is 0.1 volt. So obviously the gain is much larger than the obviously we have satisfied both conditions, the cutoff and also the saturation. Now remember what we want is emitter degeneration. So what I suggest here is, by the way, we need to check the current. Right now the drain current is about 28 milliamp. So what we can do is we can add the resistance here. At the same time, we just assume the current does not change much. And then we add the resistance here. At the same time, we raise the voltage of the gate to compensate this change. So what we can do is we can add the resistance here. Say the resistance in the source terminal is another 100. So in this case, 100 volt multiplied by 2.8, 28 milliamp. So 100 times 0.028. So it's about 2.8 volt. So what we need to do is to raise this voltage by 2.8. Originally, it is 2 volts. So 2 volt times 2.8 is 4.8. So we can make it 4.8 here. And the rest of the voltage here is 5.2. So this is the possibility. Now we are going to simulate the operating point analysis again. Make sure we satisfy both conditions. So let's do it. So now as you can see, the gate voltage is 4.8 rather than 4.9. The source voltage is 2.79 rather than 2.8. So if we do a calculation, 4.8 minus 2.79 and minus 1.9, which is the threshold, is about 0.11 volt. Now let's check the drain voltage. The drain voltage is 7.2. 7.2 minus the source voltage, which is the drain to source voltage. Let's check it. 7.2 minus 2.79. So it's much larger than the gate to source minus the threshold. So I presume we satisfy both conditions. The cutoff condition is satisfied. The saturation condition has been satisfied as well. So for the as far as the biasing is concerned, this circuit is done. So now we can use this circuit to design many things. One of the things that you will be interested is the common source amplifier as before. So we first delete this guy, and then we restructure the circuit a little bit. Now we are going to add a source here first. The source is a AC voltage source. So we connect the source here, and we label the net here input. And we are going to connect this one for it depends on what your requirement is. So I will just do this to make our life simple. So I will put 10 micro. Now the circuit is almost done. We just need the output below. So say 100K and 1 micro. So if I label the LED here as out, then the circuit will behave as before. It will work. So let's try this. So I will simulate the circuit in AC analysis. 100 and then 100 and then 0.5 gig. So I end up with a waveform window, and I position the cursor in the waveform window and then right click and then select add traces. V out over V in disappear, so it means we need to relabel to that. Oh, it's disconnected. So we just relabel to that. And then you simulate this. And then it's not here. Ah, I know now. We need a capacitance here. We need a capacitance here. Yeah, this capacitance is to block off all the DC. So I will do it again. And then so the input voltage appear now. So you got a decent bandwidth, right? And but ultimate objective is to achieve common emitter with common source amplification with source degeneration. So my suggestion here is we split this resistor. Originally, you have 100 we have 100 ohm here. So you keep this resistance. So what I would do here is I will add another resistance here, and I will delete. I will delete it like this. So I will change the resistance here. Say now we can 80, and then we make here 20. So this is the way how we achieve common source with source degeneration. And if you simulate the circuit, so this is what you are going to get. The gain is lower, but on the other hand, the bandwidth is much wider. You can even further increase this capacitance, say from 10 micro to 100 microfarads. Then the bandwidth here will be much larger. Yeah. So the core idea is uh, to vary this capacitance in a way to change the lower quantum frequency, and you will achieve a much wider bandwidth. Uh, and you can change the value. Yeah, we keep the total constant. For example, now 20 and 80 together, you will end up with 100. But you can also make it like 10 and 90. So altogether is still 20, it's still 100. And if we simulate this, the gain will be higher. So it's now 18 dB. Or equally, you can use a variable resistor here and just use the potentiometer, and then you just vary the resistance. The core resistance will remain the same, but by doing this, you will change the gain without changing the bandwidth. Okay, if you have any further question regarding this circuit, you let me know. Uh, you just leave your comments to the comment section, and I will be able to help you. Okay, thank you. Bye bye.